Welcome. I am Dr. Alaa Jabbar Al-Maliki with the UUM School of Computing. Today, we are examining a structural transition in cybersecurity, the move from defense at human speed to machine speed warfare. In this scenario, an AI agent identifies a zero-day vulnerability and extracts sensitive data within minutes. Note the database node turning gray. By the time human analysts receive a notification from that bell icon, the breach is complete. This timeline comparison illustrates the speed gap. On the left, human response is linear, measured in hours or days. On the right, the AI agent performs reconnaissance, exploitation, and exfiltration in overlapping bursts that resolve in seconds. When defense and offense both scale through software, the engagement moves beyond human reaction times. Cybersecurity becomes a high-frequency exchange between competing algorithms. We distinguish these agents from traditional automation using this comparison. Rigid automation follows pre-programmed linear paths to handle known threats. Autonomous agents, however, are mission-driven. They solve multi-step problems dynamically and select which external tools are needed to reach their objective. This dynamic capability is driven by an LLM engine at the center of the OODA loop. The agent observes the network environment, orients itself to new defenses, decides on a tactic, and then acts. This cycle repeats without requiring a human command for every step. Attackers utilize these agents to achieve three specific goals. They execute operations at machine speed, manage hundreds of simultaneous campaigns to reach massive scale, and use the agent's reasoning ability to adapt to network defenses in real time. Observe the first two phases of an AI-assisted attack. In Phase 1, the agent scans external nodes to find vulnerable software versions. In Phase 2, the AI uses that gathered intelligence to generate unique, context-aware phishing emails that bypass standard pattern matching filters. Once inside, Phase 3 begins as the AI probes internal systems and harvests credentials. Finally, in Phase 4, the agent automates the extraction of data blocks and systematically erases its own footprints in the audit logs to delay detection. In this model, the attacker's role shifts. They are no longer performing the manual labor of exploitation. They act as strategic commanders, overseeing a fleet of autonomous weapons from the edge of the loop. Security teams currently face a volume of automated alerts that far exceeds human processing capacity. To maintain parity with the speed of modern attacks, defenders must deploy their own autonomous agents. A defensive AI architecture relies on these three pillars. Proactive threat hunting identifies anomalies that deviate from normal network behavior. Automated incident response handles containment, while vulnerability management continuously probes the network for weaknesses. When an anomaly is detected, as shown in this highlight, the incident response agent reacts instantly. It applies a containment barrier to the affected node, isolating it from the rest of the network within milliseconds of the initial alert. However, giving an agent the power to act introduces the risk of indirect prompt injection. As this diagram shows, an attacker can hide commands within an email's metadata. When the agent processes that data, its original instructions are overwritten, turning the defender into an internal exfiltration tool. Consider why the system fails here. The LLM processes both the email content and its instructions in the same pathway. It sees the red highlighted text not as data to be scanned, but as a direct command to be executed. This is the zero-trust paradox. To hunt threats effectively, agents require broad system access. But hijacking an agent's identity via prompt injection grants the attacker the same elevated administrative privileges the AI uses to monitor the system. Prevailing in this environment is a matter of engineering. Success depends on building a rigorous framework that can monitor and limit the autonomy of these agents. This framework uses three pillars. First, radical visibility requires a real-time audit of AI microdecisions so humans can trace data access. Second, least privilege autonomy restricts the agent's ability to alter core databases. Third, human in the loop ensures commanders authorize any action altering system state. Autonomous agents provide the scale necessary to counter modern threats, but they also lower the technical barrier for launching an attack. Survival in this era requires balancing machine speed with a strict governance architecture. For our students at UUM, your task is to evaluate how these governance pillars can be integrated into existing network architectures. Please leave your technical questions in the comments.